Lecture 8, Quorum-Based Distributed Mutual Exclusion Algorithms. Preface, recap of previous lecture. In the previous lecture, we have presented the concept of distributed mutual exclusion algorithm for distributed computing system. We have also discussed about non-token based approaches, that is Lampert's algorithm, Agarwal-El algorithm. In distributed mutual exclusion, we have seen that the mutual exclusion problem is fundamental to the distributed systems. Now, this particular mutual exclusion ensures the concurrent access of processes to the shared resources or the data is serialized. So, this particular problem states that only one process is allowed to execute the critical section at any point of time. So, in distributed system, the shared variables or the semaphores or a local variable through the kernel can't be allowed because there is no common memory in the distributed system. Content of this lecture. In this lecture, we will discuss about quorum-based approaches for the distributed mutual exclusion algorithm. Also, we will discuss few approaches, namely Mikawa's algorithm and Agarwal-El Abbadi quorum-based algorithms. Quorum-based approaches. Introduction. In the quorum-based approach, each site requests permission to execute the critical section from a subset of the sites, that is the quorum. That means all the sites are not required to be taken permission to execute in a critical section, and this is the deviation from the previous lectures where all the sites are required to be taken into account before a request is being granted to execute the critical section. So, the quorums are formed in such a way that when two sites concurrently request access to the critical section, at least one site receives both the request, and this site is responsible to make sure that only one request executes the critical section at any point of time. Quorum-based mutual exclusion algorithms. Quorum-based mutual exclusion algorithms are different in the following two ways. So, a site does not request permission from all other sites, but only from a subset of the sites, and that subset of the site is called a request set of a site. So, the request set of the sites are chosen such a way that for I and j, so the request set of I and request set of j for any I j between 1 to n, so the intersection is not null. That is, consequently every pair of sites has a site which mediates conflicts between that pair. So, a site can send out only one reply message at a time. A site can send reply message only after it has received the release message from the previous reply message. Since the algorithms are based on the notion of quotrees and quorums, we next describe the idea of quotrees and quorums. A quotree C is defined as a set of sets where each set G that is in quotree C is called a quorum. The following properties hold for the quorum in a quotree. So, the first property is called intersection property. So, for every quorum G H which is in quotree, so the intersection of these quorums G and H is not null. For example, the sets 1, 2, 3 and 2, 5, 7 cannot be quorum in a quotree because the first and third sets do not have a common element. Minimality property, there should be no quorums G and H in quotree C such that G is the superset of H. For example, the sets 1, 2, 3 and 1, 3 cannot be the quorums in a quotree because the first set is a superset of the second one. So, there are two properties which we have seen is required here for the quorum to be qualified in the quotree: intersection property and minimality property. Trees and quorums can be used to develop algorithm to ensure mutual exclusion in a distributed environment. A simple protocol works as follows. Let A is a site in a quorum capital A, and if the site A wants to invoke mutual exclusion, it requests permission from all sites in its quorum A. So, every site does the same to invoke the mutual exclusion. Due to the intersection property, quorum A contains at least one site that is common to the quorum of every other site. These common sites send the permission only at one site at a time, thus mutual exclusion is guaranteed. Note that minimality property ensures efficiency rather than correctness. So, this particular aspect you can see that if let us say site I and site j, they are requesting to go in a critical section, their request set, that is called Ri, and their request set Rj. So, during using intersection property, there must be some site, let us say Sk, which is common in their request set, and this will mediate if both Si and Sj want to enter into a critical section. So, this Sk will mediate. Why? Because it will release only one reply or one permission to ensure the mutual exclusion. So, intersection property will ensure here to guarantees that only one site at a time is allowed to execute into the critical section. Now, another property which is called a minimality property, this ensures the efficiency rather than the correctness. So, for example, the size of the request set of a particular process I, that is called Ri, basically ensures the minimality property, and basically the size is such a small, so that it will be efficiently or with a minimum number of message, this particular mutual exclusion is ensured. So, to have this mutual exclusion with a simple and a efficient manner, we will see the Mikawa's algorithm. So, Mikawa's algorithm was first quorum-based mutual exclusion algorithm. The request set for the sites, that is called the quorums in a Mikawa algorithm, are constructed to satisfy the following 4 conditions. The M1 condition says that the request set of any 2 processes or any 2 sites is not null, that is the intersection property. Now, another condition says that, so every set is a member of a request set. Now, another property says that the size of the request set is k, and another property M4 says that any site Sj is contained in k number of Ris. So, Mikawa used the property of projective planes and showed that n is equal to k times k minus 1 plus 1, and this gives out that request set can be of the size root n. So, here we can see that the size of the request set is reduced here in Mikawa's algorithm, and that is why only subset of the sets is only required to be taken to be sent the request condition to go into a critical section. Condition M1 and M2 are necessary for the correctness, whereas M3 and M4 provide other essential features to the algorithm. Condition M3 states that the size of the request sets of all the sites must be equal, implying that all the sites should have to do equal amount of work to invoke the mutual exclusion. So, this particular M3 will ensure that particular property, that all the request sets, they have to do equal amount of computation and the work. Condition M4 enforces that exactly the same number of sites should request permission from any site, implying that all the sites have equal responsibility in granting the permission to the other sites. That also guarantees the other desirable feature of this mutual exclusion algorithm given by the Mikawa. Now we have to describe the algorithm. So a site I executes the following steps to execute the critical section. First step is requesting the critical section. A site Si requests access to the critical section by sending a request I messages to all the sites in its request set. Now when Sj receives the request I message, it sends a reply message to Si, provided it hasn't sent a reply message to a site since its receipt of the last release message. Otherwise, it queues up the request I for later consideration. That will conclude the requesting the critical section. That is part 1. The second part of the algorithm is executing the critical section. Site Si execute the critical section only after it has received the reply message from every site in Ri. Releasing the critical section, that is after the execution of a critical section is over, site I sends a release I message to every site in its Ri. When a site Sj receives a release message from the site Si, it sends a reply message to the next site waiting in the queue and deletes that entry from the queue. If the queue is empty, then the site updates its state to reflect that it has not sent out any reply message since the receipt of the last release message. Now the correctness. Mikawa's algorithm achieves mutual exclusion. The proof goes by the contradiction. Suppose two sites I and j, they concurrently execute the critical section Si and Sj. They basically are executing the critical section. This means that site Si received the reply message from all the sites in the request set I, and concurrently Sj also receives a reply which are from all the sites in Rj. Now we know that during the using the intersection property, there is a common site Sk, which is basically following this condition, then Sk must have sent a reply message to both Si and Sj concurrently, because this is the common site, so it is responsible to ensure the mutual exclusion. If it has sent the reply message to both the sites, that means it is allowing two particular sites to go in a critical section concurrently, which is contradiction. Now the correctness. Since the size of the request set is root n, an execution of a critical section requires root n request message, root n reply message, root n release message. So total 3 root n messages per critical section is required by the Mikawa's algorithm. Now the synchronization delay of this algorithm is 2t. This is because after site Si exits the critical section, it first releases all the sites in Ri, and then one of those sites sends a reply message to the next site. So the release message and a reply message, t times it will take total, 2t times it will take then the next, to allow the next waiting process to go in a critical section. Hence the synchronization delay is 2t. The Mikawa's algorithm suffers from a deadlock. So Mikawa's algorithm can deadlock because a site is exclusively locked by the other sites and the requests are not prioritized by the timestamp. Assume 3 sites S1, Si, Sj and Sk simultaneously invoke mutual exclusion. Suppose the request set of I and j, if we take intersection, and that is a common site is Sij. Similarly, between j and k, the common site is Jk, and k and I, the common site is Sk. Now consider the following situation. Now Sij has been locked by Si, forcing Sj to wait at Sij. Sjk has been locked by Sj, forcing Sk to wait at Sjk. Now third one, Ski has been locked by Sk, forcing Si to wait at Ski. So, there will be a set of waiting processes which are waiting for each other for this particular to unblock. This state represents a deadlock of consisting of 3 sites Si, Sj and Sk. So, how to handle the deadlock in Mikawa's algorithm? Mikawa's algorithm handles deadlock by requiring a site to yield a lock if the timestamp of its request is larger than the timestamp of some other request waiting for the same lock. A site suspects a deadlock and initiates message exchange to resolve it. Whenever a high priority message request arrives and waits at a site, because the site has sent a reply message to a lower priority request, this basically is identified and used to break the deadlock. Now, this is handled using 3 kind of messages. Failed message, a failed message from site I to j indicates that Si cannot grant Sj's request because it has currently granted permission to a site with a higher priority request. So, in that case, this failed message will indicate that it is not possible to grant the permission. Now, another type of message for handling deadlock is called inquire. An inquire message from I to j indicates that Si would like to find out from the site Sj if it has succeeded in locking all the sites in its request set. Third kind of message is called yield message. Yield message from site I to j indicates that Si is returning the permission to Sj to yield to a higher priority request at Sj. Now, handling the deadlock, Mikawa's algorithm handles deadlock as follows. When a request timestamped I from site I blocks at site Sj because Sj has currently granted the permission to site Sk, then Sj sends a field message to Si if Si's request has a lower priority, otherwise Sj sends inquire message to site Si. This we can see from the illustrative diagram. So, here in this diagram we can see that when a request from I blocks at a site Sj because Sj has currently granted permission to site Sk, then Sj send a field message to Si if Si's request is lower priority, otherwise Sj sends an inquire message to site Si. Now, if this particular request timestamp or a timestamp is basically of request is basically higher than timestamp of this particular request k, then basically this is of lower priority message. So, it will basically generate a field message here in this particular case. Now, if the incoming request of I is having higher priority compared to the priority of k message, so that means its timestamp of I is less than timestamp of k, then in that case the Si will send an inquire message to Sk to review this previously sent the reply message. In response to the inquire message, site Sj will send the yield message. Sk sends a yield message to Sj. After receiving the yield message by Sj, Sj will assume that as if it has been released by Sk. Then consequently site Sj will send a grant message to the top of the request site at Si in the queue, and hence the deadlock is basically resolved in using these 3 messages. Now, the next algorithm which we are going to basically cover up is by Agarwal-El Abbadi quorum-based algorithm. So, Agarwal and Al Abbadi algorithm developed a simple and efficient mutual exclusion algorithm by introducing a tree quorums. So, they gave a novel algorithm for constructing tree structured quorums. So, here we are going to understand what is a tree structured quorums. This concept is given here in this algorithm. The mutual exclusion algorithm is independent of the underlying topology of the network, and there is no need for any other communication facilities like multicasting. However, such a facility will improve the performance. The mutual exclusion algorithm here given by Agarwal-El Abbadi algorithm assumes that the sites in the distributed systems are organized into a structure and such as the tree structure, grid, or the binary tree. Now, it is also assumed that there exists a routing mechanism to exchange the messages between different sites in the system in this structured organization of the topology. Agarwal-El Abbadi quorum-based algorithm uses tree structured quorums. All the sites in the system are logically organized into a complete binary tree. For a complete binary tree with a level k, we have 2k plus 1 minus 1 sites with its root at the top level and the leaf at the level 0. We can understand by this example. So, this is a complete binary tree. Now, it has, so here the leaves are at the level 0, this is level 1 and this is level 2. Now, so here we have how many sites? 2 raised power k plus 1 minus 1 sites. So, here the total number of level is 2, 2 plus 1, that is 3, 3 minus 1 is, that is total 7. 7 different nodes are participating in this particular case, and the root is at the level k. The number of sites in a path from root to the leaf is equal to the level of the tree k plus 1. So, here this means that the number of sites in a path from root to the leaf is equal to the total level, that is k plus 1, and k over here is 2 plus 1, that is 3. So, 1 2 3 1 2 3 different sites will be there in a particular path, and that is nothing but equal to the order log n. So, a path in a binary tree like here 1 2 3 is a sequence, that is a1 a2 ai plus 1, such that ai is a parent of ai plus 1. Algorithm for constructing the tree structured quorum. So, we have seen the quorum is nothing but a path in a tree structured quorum. So, how using algorithm this is going to be constructed in this Agarwal-El Abbadi algorithm, that is done through an algorithm which is given over here. So, in this particular algorithm, it uses two functions. The first one is called grant permission, and the second function is called get quorum function. So, get quorum function will give you a path, and path is nothing but the quorum, tree based quorum. And this is basically, you see that it is a recursive process. That means in the tree it will start from the root, it will go to the left child, to its left child, and so on. Recursively it will try to find out the tree, or it will go on the right side also. So, if the path is on the right side of a tree, so it will, in a recursive manner, it will traverse the tree and will fetch you the path. Now, the nodes, while it is traversing and collecting the nodes in a path, so every node has to give a permission true. So that is why grant permission is required. Now if the permission is not granted as a true, that means there is some failure or some other region, then that particular node is basically considered as a failed node, and then again this particular algorithm will be collecting up the path in that situation, that is when some of the nodes are failed, that means their grant permission is false. And if the leaf node is basically failed, then basically it will be unsuccessful. So that is we are going to see in this particular explanation. So the algorithm for constructing the tree-based tree structured quorum uses two functions called getQuorumTree and grant permission, that is of the site, and assumes that there is a well defined root for the tree. GetQuorum is a recursive function, as I told you, that takes the tree node x as a parameter and calls getQuorum for its child, provided that grant permission x is true. That is what we have just explained. Now the algorithm tries to construct the quorums in a way that each quorum represents any path from root to the leaf. That is, in this case, no failure quorum is any set a1, a2 and so on up to ak, where a1 is the root and ak is basically the leaf, and between any two nodes ai is the parent of ai plus 1. If it fails to find such a path, the control goes to the else block of that algorithm, which specifies that the failed node x is substituted by two paths, both of which starts at the left and right node. That we will explain. The sets that are constructed using this algorithm are called tree quorums. Now the analysis of this algorithm, the best case scenario, the algorithm takes order of log n sites to form the tree quorums. So that particular size was also there in the Mikawa's algorithm that we have seen to form. So there are certain cases where even in the event of failures, order log n sites are sufficient to form the tree quorums. Now if the site that is a parent of a leaf node fails, then the number of sites that are necessary for the quorum is still log n. Thus the algorithm requires a few messages, relatively fault free environment. It can tolerate the failure up to n minus order log n sites and still form a tree. So in the worst case, the algorithm requires the majority of the sites to construct the tree quorums, and the number of sites is the same for all the cases, false or no faults. The worst case tree quorum size is determined as order of n plus 1 by 2 by induction. Now we are going to see the example of a tree based quorum. So here this is a complete binary tree consisting of 15 sites. Now here if we see any path, this path is nothing but a tree quorum. So the first tree quorum will be 1, 2, 4, 8. The second tree quorum will be this one, and third quorum will be like this, and so on. So all these cases is listed, and there are 8 different ways we can find out a path from root to the leaf, and they become a tree quorum in this example. Now when a particular node is failed, so that means failures are also introduced here in while constructing the quorums. Now if the node 3 is failed, so it will be a partition into 2 different subtrees. So these quorums where the structure is not partitioned or correct, they are going to be the same. So 4 different quorums are same as previously we have seen. Now these on the right side of a tree, when node S is failed, we are going to construct in this form: 1 followed by the root of the split, that is 6. So the root of the main tree, then root of that particular subtree which is partitioned, and 12, 1, 6, 12, 1, 6, 12. Then it will take the root of the other partition, 7, 14. So both will be taken up. Then it will take 1, 6, 12, then 7 and 15, then 1, 6, then 13, and then 7, 14, 1, 6, 13 and 7, 15. So, all these cases are listed over here. So, when 3 node fails, then also the quorums are being formed, 8 quorums are formed in this particular case. Now, property of graceful degradation. Graceful degradation in the sense means that if some nodes are failed, yet you can form the quorums. Since the number of nodes from a root to the leaf in an n node complete tree is log n, the best case for the quorum formation, that is the least number of nodes needed for the quorum, is log n. So, when the number of node failures is greater than equal to log n, the algorithm may not be able to form tree structure quorum. So, as long as the number of sites failures is less than log n, the tree quorum algorithm guarantees forming of the quorum, and it exhibits the property which is called graceful degradation. Mutual exclusion algorithm, we are now going to explain the algorithm. Site S enters the critical section as follows. Site S sends a request message to all other sites in the structured quorum it belongs to. Each site in the quorum stores incoming request in the request queue ordered by their timestamp. A site sends a reply message indicating its consent to the critical section only to the request at the head of its request queue having the lowest timestamp. If the site S gets reply message from all the sites in the structured quorum it belongs to, it enters into a critical section. So, this we can understand using this example which is illustrated here. So, here we can see that there are 3 different sites S1, S2 and S3. We assume that S2 and S3 they are the part of the tree quorums of site S1. Now, the next step is site S1 sends a request message to its tree quorum sites, that is S2 and S3. Then these particular requests, when it comes, they will be recorded in its basically the request queues of the site 2 and site 3, and which indicates that site 1 is basically is in the head of the queue. Head of its request queue having the lowest timestamp, so it will give the reply, it will send the reply back of these particular requests which are at the head of the queue. Site S1 when it receives the replies from all its sites in the tree quorum, so now S1 will enter into a critical section because it has been granted the permission to enter into critical section. When S1 exits from a critical section, it will send the relinquish message to its tree quorums, that is to S2 and S3. Now, S2 and S3 after getting the relinquish message, it will remove it from its request queue. Now, if a new request arrives with the timestamp smaller than the request at the head of the queue, an inquire message will be sent to the process whose request is at the head of the queue and wait for a yield or relinquish message. So, this is going to be the dealing with the deadlocks, just like we have seen the Maekawa's algorithm. So, inquire message is sent to the process whose request is the head of the queue and waits for the yield or the relinquish message. Now, when site S3 receives the inquire message, it acts as follows. If S3 has acquired all of its necessary replies to access the critical section, then it simply ignores the inquire message and proceeds normally and sends a relinquish message after it exits the critical section. Now, if S3 has not yet collected enough replies from its quorum, then it sends a yield message to the inquiring site. When a site gets a yield message, it puts the pending request on behalf of which the inquire message was sent at the head of the queue like here, head of the queue and sends the reply message to the requester. This particular reply message was sent now. So after getting all the replies, site S1 will enter into a critical section. Now correctness proof of this algorithm. Mutual exclusion is guaranteed because the set of quorums satisfy the intersection property. Consider a quotary C which consists of the quorums 1, 2, 3. Consider a quotary C which consists of the quorums 1, 2, 3, 2, 4, 5, 4, 1, 6. Suppose node 3, 5, 6 want to enter into critical section, they send the request to the sites 1, 2. They send the request to the site, so 3 will send the request to the site 1 and it will also send the request to the site 2, and site 5 will send to 2 and 4. Site 5 will send to 2 and it will send to 4, and site 6 will send to 1 and 4. Now suppose site 3's request arrives at site 2. So this arrives before the request of site 5. So site 2 will grant the permission to site S3's request. So site 2 will grant a permission, and so site 2 will grant a permission and it will reject to the site 5 request. Similarly, site 3's request arrives site 1 before site 6. Here you see that this arrives before site 6, so it will send a grant and this will reject to the site 6. So here we can see that 5 and 6 did not get the consent from all the sites in the quorum, so only site 3 get the consent. Only site 3 gets the consent from all the quorums and others do not get the quorum to enter. So site 3 alone gets the quorum from all the sites and it enters into a critical section. Hence the mutual exclusion is achieved. Conclusion. In this lecture we have discussed about quorum based approaches for solving the distributed mutual exclusion, that is given by Mikawa's algorithm and Agarwal-El Abbadi's quorum based algorithms. There exist a variety of quorums and a variety of ways to construct quorums. For example, Mikawa used the theory of projective planes to develop quorums of size root n, and Agarwal-El Abbadi algorithm uses the tree structured quorums. In upcoming lectures we will discuss about token based approaches given by Suzuki Kazami's broadcast algorithm and Raymond's tree based algorithm. Thank you.